All right, so after learning about the photoelectric effect and the Broglie wavelength and wave particle duality, we're ready to revisit the Bohr model and try to understand how Bohr came up with the idea that electrons exist in defined energy orbits, and try to make sense of Rutherford's model of the electrons, which said that electrons are like satellites around a positively charged nucleus. And what kind of evidence did Bohr have to make this model? We've actually done these calculations for these energy transitions of emission spectra and absorption spectra before in topic 7. But what we're doing in the higher level section is we're trying to really define how Bohr came up with this model and prove that it would be true. It's nice to come up with a cartoon picture, but what kind of evidence did he have to prove that this is true, and how could he actually predict these particular wavelengths that would appear on an emission spectrum? So Bohr was a very young Nobel Prize winner, very bright mind that worked with Rutherford right out of high school basically, and did some clever algebra to win a Nobel Prize, which is kind of one of my favorite things to look at in the higher level section. So how did he come up with the math to prove that this is true? And that's what we're going to do. So Bohr came up with these observations from the emission and absorption spectra that only quantized amounts of energy are absorbed and emitted. That's what we learned in topic 7. And that electrons exist in defined energy orbits. And if they absorb very specific wavelengths or frequencies of light that correspond to the energy differences between these levels, that would be the only way that those electrons can hop. So atoms don't absorb random amounts of energy. That would have been predicted by Rutherford's model. Atoms absorb very defined amounts of energy, which is why we have these lines in an emission and absorption spectrum. So understanding the hydrogen emission spectrum, before actually Bohr did anything, a bunch of teachers and just mathematicians, they love to read science, they weren't really scientists, but there was a teacher in Switzerland by the name of Bohr, who liked to do puzzles. And he was reading literature, and he came up with an actual mathematical formula to understand the relationship between these wavelengths. And this is his formula. So first of all, they had the evidence when you shine light or you heat up an atom and shine that light through a diffraction grating, you'll get these emission lines. And what Balmer found was this relationship when he graphed 1 over the wavelength versus some imaginary construct that he randomly created over here, where n in this case is n it can be whatever level this is, 1, 2, or 3, and m is any level greater than 2, so m is any integer larger than 2. Balmer was able to put these numbers in here, make a graph, and come up with a constant, a linear relationship named the Rydberg constant, which is 1.097 times 10 to the 7 per meter. And if I plug numbers in, I would be able to predict these particular wavelengths. You'll have this in your text. So for an example, to predict a wavelength of light emitted from level 3 to level 2 when it's excited and moves back down, we can use that formula that we have over here to be able to predict the wavelength of light that comes off. So as you can see here, I've shown the formula. I've plugged the numbers in. This is the second energy level. This is the third energy level. And if I multiply that through and do the inverse of this answer, I get 656 nanometer light, which actually corresponds to this red wavelength. So Balmer was able to come up with the equation only for the visible wavelengths of light. Beyond visible, we have UV wavelengths and we have infrared. And if you do some research about these series, if you're in chemistry, you would see the Lyman series and other series. Those correspond to different values of M and N. And those would be wavelengths that you can't really see. So they had to wait a little bit longer to find those wavelengths of the infrared and the UV for those chemistry students that are here. So again, just to summarize, since he was able to do this, he was able to show that there's math that relates to this and there's a constant. The Nobel Prize is in the waiting. If we could actually find a theory and math that can explain this constant and explain this relationship, we'd have stronger evidence as to why the electrons exist in these defined orbits. And that's what we're going to be doing over the next few video lessons, is we're going to see how Bohr defined the math to find that constant and define this relationship and prove that mathematically and physically, using physical models, that he can explain how that model exists. So just as a reminder, when an excited electron relaxes from a higher energy state to a lower energy state, it emits a photon, and the change in those energy levels corresponds to the product of Planck's constant times the frequency of light, or hc over lambda. And what we'll see later on is that we can actually calculate the energy of each orbit. We've done this in chapter 7 or topic 7 using this equation. And this equation is after Bohr did all his work. Bohr was able to define this equation. The energy actually of each level is negative 13.6 electron volts divided by the energy level squared. So the lowest energy level, the ground state, is negative 13.6 electron volts. And all the other energy levels are defined by this equation. And if I subtract those two energy levels and relate it back to this, I can calculate the wavelengths that are in those series. So Balmer series is over here. The Lyman series, which has more energy, would be more UV light oriented, is over here. And so all these scientists are working together, and not just scientists, but teachers, to come up with a mathematical model to prove that this exists.